It is a peak detector circuit. So as the name signifies, it is used to, or it is employed to display the peak value of a voltage waveform. So when we apply voltage of a particular threshold value which is non-sinusoidal in nature, it cannot be detected with a voltmeter. Therefore, we make use of this circuit called as peak detector circuit. So what is the primary utility of a peak detector circuit? You can note down. It is used to measure the peak values of non-sinusoidal waveforms. So we can have triangular waveform, or we may have a square waveform or a rectangular waveform other than a sine waveform, right? So generally, when we measure the voltages, an AC voltmeter or a conventional AC voltmeter, as I told you previously, a conventional voltmeter cannot measure non-sinusoidal waveforms. So this is the limitation of a voltmeter. Therefore, we switch to the peak detector circuits, right? Because generally the AC voltmeter, it is measuring the root mean square value of pure sinusoidal waveform. This you know. Therefore, peak detector circuit provides us the possible solution of measuring the peak values. So it is used for measuring the peak value of non-sinusoidal signals. Now let us have a glimpse into the circuit of this particular apparatus or device. So we'll make use of an op-amp as we are using currently. So we are using an op-amp in the following configuration. We have a diode which is connected in this manner. And on the input side, we have a resistance which is connected in a closed loop. In this manner, this is the non-inverting terminal, and across this we have connected a resistance which is known as compensation resistance ROM. To this we are applying the non-sinusoidal waveform. Here we have taken example of a square wave as input. So we have applied a voltage source which is non-sinusoidal in nature, and this resistance is normally taken equal to R. This is called as the compensation resistance, ROM. This is the compensation resistance, and here we are connecting another diode. We can number the diodes: D2, D1, and here we have a capacitor which holds the charge. That means the output produced at this point is developed across the capacitor C, and this appears as the output voltage V0. So V0 is the output voltage here, RL is the load resistance, and this is the capacitance C. Okay, now we can draw the corresponding waveforms for this, and then we can discuss the operation of this circuit, how it works. So let us discuss the operation part of this. So the principle of operation or the operation steps, how it works, we will break the operation into positive and negative half cycle. So for positive half cycle, in this case means when the input is this. So when the input is going in the positive direction, what is the status of the circuit we are going to discuss. So let us name this input voltage as Vin. So for the positive half cycle of input voltage Vin, as we see, this is the non-inverting op-amp because the input is applied at the non-inverting end. Therefore, when the input voltage saturates in the positive direction, the output also saturates in the positive direction like this. The polarity of output is positive, because of which here we have a plus sign, and in this case diode D1 is forward biased while diode D2 is reverse biased. D2 is at this point of time is reverse biased. Am I audible to all of you? Am I audible to you? Okay, so D2 is reverse biased, and when the output goes from this side, a current is produced here at this point. At this point of time, a current is developed when this diode is forward biased. Due to this, the capacitor starts charging. So capacitor starts charging to its full value, that is peak value of the voltage. So at this point of time, capacitor C charges.
सर एक बार फिर से बता दिए सर.
Right. So you look at the circuit. If you look at the circuit, it is a non-inverting amplifier because the input voltage is applied at the non-inverting terminal. If you see here, this is terminal 2, this is terminal number 3. Terminal 3 is the non-inverting terminal of op-amp, and terminal 2 is the inverting terminal. Here the output is derived at terminal number 6, as I have discussed with you earlier. Now what happens? We can imagine we can break the input cycle. This is the input waveform. The input waveform can be broken into two intervals, 0 to pi and pi to 2 pi. Now we are discussing the timing 0 to pi. That means we are discussing this particular duration or this instant here. So we are discussing this particular instant. So at this point of time, since we know that a non-inverting amplifier, the input and output voltages are in phase. Therefore, when the input voltage progresses in the upward direction, the output will also progress in the upward direction. It means that if the input increases in the positive direction, the output will also increase in the positive direction. Because of this, the polarity of the output here will be plus, and because of this, the diode D2 will be reverse biased, since the positive pole or the positive potential is connected to the cathode of the diode D2, whereas the positive pole of op-amp is connected to the anode of D1. Therefore, D1 is forward biased. At this time, when the current is produced, it builds up the charge in the capacitor, and the capacitor charges peak. So it charges to the peak value. If I say that Vp is the maximum value of the voltage, input voltage, you can imagine if I take Vn equal to 5 sine omega t, what is the peak value then? Peak value is 5 volts. So this is your Vp. So our capacitor will charge up to, I'm just taking as an example. So our capacitor will charge to 5 volts and it will retain the charge. So this is when the positive cycle is there. Now we will discuss the negative half cycle. Second will be for negative half cycle. What is going to happen? Can you tell me what will happen in the negative half cycle of Vin?
D1 off हो जाएगा.
Exactly. Now look at the circuit. Now what will happen at this point of time? Now we have this end of the waveform being applied to the circuit. Now at this time this waveform will go to the circuit, and this is interval pi to 2 pi. This is the negative half cycle. Because of this, since this is negative, the polarity developed at the output will also be negative. So the polarity at this point of time will be minus. Now it won't be plus anymore, it will be minus. Therefore, because of this negative terminal is connected to cathode of D2, it will be forward biased, and this diode will be reverse biased, right? So what will happen? Opposite will happen now. D1 will be reverse biased, and diode D2 will be forward biased. Right. Now because of this, you can imagine that this track will be broken here. Now this track won't be there. So the modified circuit will look like this. This portion will be broken here, and now the capacitor has attained its full charge. Now what will capacitor do? The capacitor will start discharging across the resistance. It will discharge its energy across the resistance, right? So at this time the capacitor will start across RL. So RL is the load resistance here, right? Now why will this happen? Because capacitor has only one path. The current cannot go here because this is an open circuit here. Open circuit because diode D1 is reverse biased. And now one condition which is to be satisfied, I am going to write that for the proper operation of the device, conditions to be satisfied, you should know one thing, that we are concerned with the charging and discharging time period of the device. Generally, the charging and discharging cycles should match each other. So in this case, the following conditions which are to be satisfied: C into RD should be less than or equal to T upon 10. Right. So C into R or C into RD is the resistance of forward, where RD can be taken as the resistance of the forward bias diode. This is the forward biased diode resistance, or this is the forward resistance of the forward bias diode. So this is called a charging time constant. What is charging time constant? Charging time constant is applicable to the situation when the capacitor is charging. So in the charging path, two components are coming into picture. One is the resistance of diode D1 and another is the capacitance C. So we have mentioned C into RD should be less than T upon 10. What is T upon 10? If this total time period is T, if this is T, then it means that the capacitor should charge in a time interval equal to 1/10 of the total time period. So the capacitor charging should be very fast. This condition has to be satisfied. Let us mark this as condition number 1. Right. We have mentioned the meaning of R. T stands for the time period of the input waveform. As I have told you, it is the total time period of the input waveform. Okay. So another condition. This is when we are talking of charging. This is called a charging time constant. There are two types of constants. One is charging time constant, which is applicable to the situation when the capacitor is charging. It is equal to the product of capacitance C multiplied by resistance. So generally in the charging path, these two components, capacitor and resistance, they are coming in picture. Similarly, we have another constant which is called as discharging time constant, which is to be satisfied again during discharge. capacitor and load resistance come into picture. If you look at the circuit, जब discharging होता है, so during discharging period, which two components are coming into picture? One is capacitor C, and it is discharging across the, so they form a closed loop like this. So we have capacitor on one side and resistance on another side. So their product C into RL, this is called as discharging time constant. Is it clear to all of you? This is called as discharging time constant. Alright, this should be greater than or equal to 10T. This is generally applicable to filtration circuits. Generally we say that it implies that when a capacitor is fully charged, it will not discharge up to 10 charging cycles. That means once the capacitor is charged thoroughly, it is charged to its threshold value, it will not discharge up to 10 cycles, which is a figure of merit. Like you can imagine in the case of rectifier circuits, if you know, when we have output of a rectifier circuit and we are using a filter, then the filter does this action. The action of filter is like this. What is the role of a filter? The filter does not allow the waveform to go down. It smoothens the output like this. Therefore, our output looks like this. Our output becomes like this. It is an approximation of DC. Alright, so this is called as discharging time constant, and discharging time constant should be quite large. It should be 10 times the total time period of the, suppose you don't want the resistance value, RL should be very high. It is of the order of, in order to keep the value very high, RL should be of the order of 10 kilo ohms, because what do we want? We want the product C into RL to be greater than 10 times T. For that purpose, we have selected the value of RL as a standard value equal to 10 kilo ohms. Is it clear?
Yes sir. Sir, charging time constant में लोड रेजिस्टेंस वाला पाथ भी तो होगा सर?
ना, चार्जिंग टाइम कांस्टेंट में देखिए क्या होगा, चार्जिंग में लोड रेजिस्टेंस का होगा, लेकिन हम अभी बात कर रहे हैं कैपेसिटर की, और ये लोड और रेजिस्टेंस जो कैपेसिटर है दे अपीयर इन पैरेलल सर्किट. तो यहाँ पे अगर हम देखें तो दीज कंपोनेंट्स सी एंड आर दे अपीयर इन अ पैरेलल सर्किट, एंड एट दिस टाइम the current flows in such a manner, it flows to this, because if you look at this circuit, if I redraw this circuit here, during charging what is happening, diode D1 is forward biased, so you can imagine that there is a tiny resistance which is very small. This we have mentioned as RD, which is the forward resistance of the diode. Then we have a capacitor which is charging, and across this there is a load resistance RL. Right now, as I told you, when the current flows from this side, it is an alternating current. What is the nature of the input voltage source? Is it alternating or it is DC, direct source? It is an alternating source, right? So the output is also alternating in nature, and you know that capacitive reactance for alternating voltages is less. So what is the formula for capacitive reactance? 1 upon 2 pi Fc, and for alternating voltages F is large, therefore Xc is small. What does it mean? It means out of the two options, suppose the current has to flow, if current I is coming, which path will it select? It has got two paths. One path is through capacitor, another path is through resistance. Which path will it select? What will be the preference? It will be through the capacitor. Why? Because the capacitor is offering least resistance. Current always selects the path of least resistance. Therefore, during charging cycle, the current does not flow into the load. Instead, it flows through the capacitor. A low, small, very tiny portion of current flows into the load, which is negligible. So that is why during charging, we don't take the load resistance into account. We take into account only the forward resistance of the diode, which is very less. It is generally the forward resistance of the diode is of the order of few ohms. It is of the order of 20 ohms, which is very less. Generally we represent it by RF or RD. Here we have mentioned it as RD. Is it clear now? Okay, so what we have understood from the circuit is that it is a peak detector circuit, and now we will see how the peak is detected through the waveform. We will draw the output voltage waveform for this, and then you will have a glimpse, or you will develop an idea how the peak detector builds the peak, how it detects the threshold of the signal. Right, I am going to plot the waveform here. On the upper side we have the input waveform, on the lower side we have the output voltage waveform. So this is the input side, V in, and here is the output, V naught. So the input waveform, as we have seen, we have noticed, it is a square waveform. So I am plotting the waveform here. You can draw the waveform yourself with proper scale. So this is the input side waveform, which is a square waveform, and corresponding to this we have output voltage waveform. You can extend the input waveform. The input waveform is also known as the mother waveform because it happens to be the reference waveform for all types of computations. If we have to plot the output waveform, we have to take a reference of the input waveform. That means we have to take the projections of the input waveform in the downward direction, as I am doing here. You can also do it in the same manner. So with respect to time axis, we have plotted the waveforms. Time is the reference axis, and now the waveform that we get out of here is a rectangular waveform. So is a triangular waveform because we are using a capacitor. So because of the capacitive effect, we are getting the threshold of the waveform. So threshold, we can have an eye on this 1, 2, 3, 4, 5, 6. So this type of waveform is obtained. So these are the peaks, or these points that we get here. This is representing the peak value of the applied input voltage. You can designate it by Vp here. You can mark a point Vp on the left side, and T is the time period. So you can imagine that the capacitor, once charged, it will not discharge up to 10 input cycles. Right. So these are the input and output waveforms for a peak detector. So this is a small circuit, but it is very important since we can obtain the threshold values of a non-sinusoidal signal also using this circuit. That's why this is called as a peak detector, and using the concept of op-amp, we can obtain the threshold or peak value for a given signal. Right. So here we have applied the threshold value for this particular signal, which is designated as V in. Right. And in this case, the circuit behaves like a voltage follower. When the diode is forward biased, when D1 is forward biased, it is just like a closed loop here, and it behaves like a voltage follower in that case. And you know the meaning of voltage follower. Voltage follower produces an output which is a replica of the input. The voltage gain of this circuit is closer to 1. Right. Next circuit that we are going to take up after this